InfCam, infinite homography conditioning for camera-controlled video generation. From a single video, we re-render the scene along any target camera trajectory. And we do it entirely without depth estimation. Prior methods rely on reprojection. Lift pixels to 3D with estimated depth, then reproject to the new view. But depth is never perfect. Errors produce holes and stretched artifacts in the reprojected frame. And no gradient flows back to the depth network, so these errors can never be corrected during training. The generator is conditioned on this corrupted signal and inherits its artifacts. Our key idea: decompose the camera motion into rotation and translation. Rotation is a pure 2D warp, the infinite homography, and needs no depth at all. What remains is only the residual parallax, bounded to a short segment on the epipolar line, a far easier depth-free target. InfCam builds on a video diffusion transformer. Source and target latents enter the DIP blocks. The core is a homography-guided self-attention layer, attending across source, target, and a homography-warped latent. The warping module applies infinite homography warping and encodes the camera pose for translation. The two are added and fed to the attention layer, which models the remaining parallax. Only the newly added modules are trained. The pre-trained backbone stays frozen. Rotation is handled for free, so the model only learns the small residual parallax. Existing datasets are biased. InfCam video places cameras at different viewpoints, but each stays static, with no camera motion. Multicam video adds trajectories, yet keeps fixed initial poses and a single focal length. So we build augmented MCV, augmenting trajectories with varied initial poses and focal lengths. On synthetic benchmarks, InfCam follows the target trajectory faithfully. Baselines drift, warp, or hallucinate content as the camera moves. On real WebVid clips, our results stay sharp and geometrically consistent. And on In the Wild videos, InfCam preserves structure where reprojection-based methods break. Across all cases, higher pose fidelity with fewer artifacts. The numbers agree. On augmented MCV, InfCam leads on PSNR, SSIM, and LPIPS, for both shared and different intrinsics. The same holds on WebVid, with especially large gains in camera pose accuracy. In summary, InfCam achieves precise camera control by encoding camera rotations in the latent space and learning the residual parallax. Our augmented MCV dataset removes the trajectory and focal length bias of existing data, helping it generalize from synthetic to real-world video. Thanks for watching. Code, paper, and more results are on our project page.